For linear systems that are quite large, it's more efficient to reduce the augmented matrix to row echelon form, which is the Gaussian elimination step, and then follow this by back substitution to solve the system, rather than doing the Gauss-Jordan elimination to get the system in reduced row echelon form. So consider our previous example, where we reduced the augmented matrix to row echelon form. So our system is x1 plus 2x3 plus 5x4 is equal to 3. And then we have x2 plus 2x3 plus x4 is equal to 5. And then we have x3 plus 5 on 2x4 is 15 on 4. So the first step is working from this row echelon form of our system and solving the equations for the leading variable. So our leading variable is x1. So we have 3 minus 2x3 minus 5x4. And in the next equation, our leading variable is x2. So we have 5 minus 2x3 minus x4. And then x3 is 15 on 4 minus 5 on 2 x4. And now we start from the bottom and substitute each equation into the equations above it. So therefore x1 is equal to 3 minus 2 by x3, which is 15 on 4, minus 5 on 2x4, minus 5x4. So we can see that this simplifies to 3 minus 2 by 15 on 4, which is 3 minus 15 on 2, and 3 is 6 on 2. So what we get is minus 9 on 2, and then we have plus 5x4 minus 5x4 is 0. So we solved for x1. And substituting x3 into x2, we get 5 minus 2 by x3, which is 15 on 4, minus 5 on 2 x4, and then minus x4. So what we have is 5 minus 15 on 2. So that will be 2 by 5 on 2, which is 10 minus 15 on 2, or minus 5 on 2. And then we have 5x4 minus x4 is 4x4. And this is our final step, because we can't really substitute x2 in x1. So now we'll write down our solution so far. And the final step is to assign arbitrary values to the free variables. So in this case, we have x4 being the free variable. So we'll call that the parameter t, where x4 is equal to t. And therefore we can assign arbitrary values of t to get infinitely many solutions. And this is the same result we got using Gauss-Jordan elimination.